All right, welcome back again, everybody. Today we're going to be doing what I consider an amazing section. It's the last section of chapter 15, 15.9, which is all about the change of variables formula for multiple integrals. Um, this section, it encapsulates so many things that you have seen previously, like from Calc 1 and Calc 2 and this class, and just gives you a general result that holds for multiple integrals. That's just really, really amazing. Let me pull up the slides and I'll get started. I don't want to just stand here rambling the whole time. Okay, so 15.9. First off, just a fair warning, this lecture will most likely be a bit of a long one. As you can see, there's a lot of slides. There's just a lot to cover. So here's the overview. I'm going to talk about content a little bit, just a note about the content of this section, what's in this lecture versus what's in the book. We're going to get a motivation for the content of this section, like why we care, what we're doing. We're going to recall some not properties, some theorems that you learned previously in Calc 1 and Calc 2, and in particular the inverse substitution rule, because that's kind of what we're generalizing in this section. Then we're going to talk about transformations, important properties of continuous transformations that allow us to do the things that we're going to do in this section. Then we will get the general change of variables formula in double integrals. And then about midway through there, we're going to stop and talk about the Jacobian matrix, which is necessary for this construction. Um, then we will generalize the result to a change of variables in triple integrals, and then a change of variables in multiple integrals is where we'll finish up. All right, so if you need to take a break in the middle of the lecture, please do, don't feel bad. But there's going to be a lot of stuff we have to talk about. Okay, so yeah, first a little bit. So in this section and then several sections of chapter 16, the specific content of my slides and my lectures will deviate from that which is in the textbook a little bit. I do this to give a more complete or more intuitive or more accurate picture of the concepts. One of the things that I love about Stewart, Watson, and Clegg's book is that it has everything for everybody. It's a gigantic book that just works for so many different types of calculus classes. It's just really, really good. It's very thorough. It's very complete in general, but sometimes when you have that much information packed into a book, the narrative of particular sections isn't communicated as well as some of us might like. So, for example, the examples that I use in these slides and in these lectures are from that book, and the figures and the content is basically the same as what's in the book. But there are some times where I like to come in and add some more clarifying information or just some more general information that the book may not use. So for example, in this section, the book makes use of several important theorems without mention because they probably don't want to like go into it. But they use these theorems without mentioning them, and they really should be at least mentioned because they're necessary to produce the results that we're talking about. It might even conflate some definitions at times. This is just a convention issue. No offense to Stewart, Watson, and Clegg, but it can lead to confusion when certain definitions are conflated as like the same thing. Um, and it can lead you to an incomplete understanding of what's going on. So for this particular lecture and these particular slides, I encourage you to follow these slides, this lecture, and ask questions in class, because there's going to be content in here that the book does not address, but it does use tacitly. So just bear that in mind. Okay. So here is the motivation for the section. If you remember back in Calc 1, we developed a very handy integration technique called the substitution rule. This is a U sub, right? Everyone's favorite integration technique. It's like the easy one. It's the one that you learn first. Most often you learn it in Calculus 1. It's just a great rule, right? Great theorem. Then in Calc 2, you develop another handy integration technique that's actually called the inverse substitution rule. So in this textbook, it's section 7.3, and primarily we used it for trigonometric substitution. So if you go and you look in section 7.3, there's a very, very brief discussion about how this is an inverse substitution, and this is the inverse substitution rule. And then the rest of the section is basically devoted to using it for trigonometric substitution. So what I'm trying to say here is that trigonometric substitution is a special case of an inverse substitution. And what's happening here is you're just doing a change in variable for your integral. In both of these cases, whether it's a forward substitution or an inverse substitution, you're performing a change of variable. And now what we're going to do in this section is we're going to generalize that process considerably and just beautifully. The result really just is very beautiful, in my opinion. So quick review, quick recall, right? So hopefully this is very familiar. This is from section 4.5. This is the substitution rule. So just a review, this is what it says. If u of x is a differentiable function and u prime is continuous on the interval a to b, and f is continuous on the range of u, then you can perform this substitution and you can convert your integral into an integral with respect to u. So this is just the substitution rule. If you don't remember these technical details, that's okay. This is what you were doing, right? You were basically making a substitution and altering the integral so that hopefully the new integral is easier to evaluate. That was the goal. Now, in section 7.3, that's where you learn the inverse substitution rule. And when I cover this section, I actually go through it with a little bit more completeness than they do in Stewart's book. So if you want to watch my lecture on section 7.3, these slides are kind of the same slides you'll see there. Really, I just want to emphasize what's happening when you're doing an inverse substitution, right? It gets used in the context of trigonometric substitution in that section, but what you're really doing is a more general technique called an inverse substitution, all right? So here's the setup if you haven't seen this before. Suppose we want to evaluate this integral. What we can do is we can actually substitute for the input variable x with some function g of t, as long as g is a differentiable function that's one-to-one. So the one-to-oneness is what gives us invertibility. So as long as we're picking a differentiable and one-to-one function, the function will have an inverse and we can do this substitution, right? So if we have this integral, let's let x equal g of t with those conditions. When x is equal to a and x is equal to b, so in other words, the bounds of integration, we can write these in terms of t. See, we're doing a change of variable here. When x is equal to a, that means t is g inverse of a. And when x is equal to b, t is g inverse of b. So we've now converted our upper and lower bounds, or I should say upper and lower bounds, to be in terms of t, our new variable, our new independent variable, instead of x. We also have this, because g is differentiable, dx dt is equal to, or I should say dx is equal to g prime t dt. So basically, if you differentiate this, dx dt is g prime of t. Now we can substitute everything in. We can substitute in our value for x. We can substitute in our values for a and b. We can substitute in our value for dx. And we convert this integral into this new integral here. There we go. And that is the inverse substitution rule. We have performed an inverse substitution. Here it is written in just a nice clean way. If f is continuous on a to b and g is a differentiable and one-to-one function whose range is a to b, then we can rewrite this integral like so. And just to clean things up a bit and to reveal a little bit more structure that we're going to see very, very frequently in this section, we're going to do this. Let's just let g inverse of a be c and g inverse of b be d. We're just relabeling them. So then we can rewrite these as c and d. And what I also want to point out is that, remember, g of t is equal to x. So we can just call it x of t, right? X is equal to g of t, so we can just label it as x of t. So this becomes this. And what is g prime of t? It's dx dt, so you get this right here, right? So what I want you to do here is just take note of the structure of this integral that you see here for single variable functions, all right? That's the structure we've got there. And we're going to see the structure again. All right, so back to the motivation. We've already seen two important specific uses of this substitution rule and changes of variables. We saw it in polar coordinates. We saw the same thing in cylindrical coordinates, and we also saw this happen in spherical coordinates. So what's happening is we are making a change of variable, and we are observing how that alters the integration, how that alters the integral itself. Now what we're going to do, we're going to generalize this process to any suitable transformation, all right? So here is where I'm going to go a little bit more above and beyond what the book does. So we're going to talk about transformations, get some important definitions and some important theorems, all right? So the book may or may not contain this information. What is a transformation? Just to start, a transformation T is a function that takes a region in space and deforms it into another region via some rules applied to the components. So intuitively, what you can imagine is if I had some region in space and I have a function that operates on that region, it will deform that region into something else. All right. And that's really all we're talking about. We're talking about taking a region and deforming it in some way. That's what a transformation is doing, right? Let's just focus on double integrals for a moment, and let's develop everything for double integrals, and then we'll generalize as we go along. So if we want to consider a change of variables, what we're doing is an arbitrary change of variables, or somewhat arbitrary. We're going to consider a transformation T that goes from the plane to the plane, but it's going to go from the UV plane to the XY plane. All right, so this is the first time we've really seen anything like this in this class so far. So give yourself a minute to think about what this means. I'll throw up the thinker in just a minute. But what I'm saying is we have this function T, and it takes the point u comma v and maps it to the point x comma y under some parametric function rules. So x is equal to some function of u and v, y is equal to some function of u and v. So if you plug in u and v to these functions, it gives you a result. It gives you a point as an output. So think about that for just a minute. Let me throw up the thinker and really just read this a couple times, ponder it for a minute, and try to make sense of what I've said so far. This is actually a good time to say something out loud as well. Remember, you don't have to say it to anybody, just say something out loud to yourself so that your brain can get that feedback, and that helps you see if something is really clicking or not. All right, so one thing about this particular construction that is new is that our function t is a function from a plane to a plane. So it's not a real valued function, it's a vector valued function. It's essentially describing how you would transform a vector. All right, so for those of you that are taking linear algebra, this might sound very familiar. That's basically what we're talking about here, except in linear algebra, the transformations that you study are linear. They're linear transformations. Okay, so now we need to talk about some properties and some definitions related to transformation. So here's the first one, the image of a transformation. So if we have a transformation T and T of U1, V1 is equal to X1, Y1, then we call the point X1, Y1 the image of the point U1, V1 under the transformation T. Okay, so basically the output point is called the image under the transformation. So we take U1 and V1 and it goes to X1, Y1, right? And X1, Y1 is the image of this point. So what's happening here is T is transforming a subset S in the UV plane into a region R, which is the image of S in the XY plane. So T of capital S, that is the image of the region S that we started with. And I've got some figures in just a moment here, but that's really what it is. T of S is the image of S. In this case, it's actually equivalent to the range. This is the range of T. All right, so R is the range of T. And you're taking this region and you're mapping it to this region under this transformation. Okay, very, very general idea. The next definition is a one-to-one or an injective transformation. So given a transformation T, T is said to be one-to-one or injective if no 2 points in the domain have the same image. That's really what it means. This is the same definition that you saw before anytime you talked about inverse functions in the past. So at some point you had to have studied inverse functions, and I'm sure every one of you has seen this before. The definition is the same. It's really just the same thing. It's a one-to-one function. Now, on the other end of things, you can talk about onto transformations or surjective transformations. And these things are, I'll just read it here. So a transformation T is said to be onto or surjective if and only if every point in the codomain has a pre-image in the domain, right? Some of you may not have heard the phrase or the term codomain before. I know that I introduce it in my pre-calc and my calculus classes because it's relevant. So what is the codomain? You can think of the codomain as the place where the range lives. That's really what it is. The codomain is, well, for us, I'll give you an example here. Let me go back. Here we go. So for our transformation T, the codomain is R2. So that's the plane, right? The whole plane. The codomain is R2, but that doesn't mean that R2 is the range of the function, right? So the range can be different from the codomain. The range of this function usually lives inside the codomain somewhere. It's usually not equal, right? So here, if you think about this picture here, T maps S to R, and what I'm saying is that this new region R may not be the entire space where your function maps to, right? That's what I'm saying here. So an onto function, a surjective function, is one where that is true. So it means if you pick any point in the codomain, then there is some preimage of that point that lies in the domain, so that T takes that point to the image you selected, right? So a little note I have here, every transformation maps onto its image, meaning if you pick a point in the image of your transformation, there's obviously a pre-image. That's like, picking a point from the range and looking backward, right? Lastly, what is a bijective transformation? A bijective transformation is just one that has both of these properties. It's both injective and surjective. So it's one-to-one and it's onto. That's what bijective means. Okay, let's look at some pictures. So the picture can help things a bit here. Just to start with this, let me zoom in. Here we're on the UV plane, and we've got a region S in the UV plane. And what we're going to do is we're going to map that region S to a new region R under some transformation T. Call it T. So T takes all the points in here and maps them to points over here. That's the idea. So the picture shows here, T takes the point U1, V1 and maps it to the point X1, Y1. This is the image of this point right here, the image of the point under T. All right, that's the idea. And now notice here we're in the XY plane, right? Now, if T is an injective transformation, if it's one-to-one, then that means it admits an inverse transformation. There's an inverse transformation, which we denote by T inverse, that goes from the XY plane back to the UV plane. And if that's the case, then what we can do is we can invert the functions that are going this way, and we can have inverse functions that go backward, all right? So let me zoom in on the picture again. Here's the point X1, Y1. T inverse, so the inverse of T, takes this point and maps it somewhere over here. That's T inverse, going backward, quite literally, all right? So as long as your function's one-to-one, you can do this. So if your function is one-to-one, then you can invert the functions, and you can write the function u as a function of x and y. So now it's literally you put in x and y, and you get out a u. You put in x and y, and you get out a v, like so. So where you're coming from and where you're going, I'm forward directions, forward directions, backward directions, that becomes important in this section, and just generally whenever you're working with functions. Right. So in this course, we typically assume that our transformation T is a C1 transformation. That just means that it's got a continuous derivative, or in other words, it's continuously differentiable. So that means that x and y have continuous first partial derivatives. That's what C1 means. The one corresponds to how many orders of derivatives you have. So C2 would mean you've got continuous second order partial derivatives. But remember that continuous partial derivatives imply differentiability, and so that also means that T is continuous since differentiability implies continuity, right? This is from, oh geez, what section was that? Oh geez, the chain rule section, I think? No, the one right before, 14.4. Anyway, so yeah, as long as your partial derivatives are continuous, then your function is differentiable at a point there, at that point where they exist and they're continuous. Yeah, no, that's it. So, all right. The assumption that T is C1 allows us to employ the following non-trivial but very, very helpful theorems, which the book uses without mention. So this is something that the book is appealing to in its examples and its discussion about transformations, but it is not outright stating them. And I feel that it's important to state these results because they're non-trivial results. They're important. They're non-trivial. So here's one. This is an important one. If T is a continuous transformation, then the image of any boundary point of a region S is a boundary point of the image of S. So in other words, boundary points go to boundary points under your transformation T as long as it's continuous. Okay, that's an important result. If you've got a continuous transformation, your boundary is going to go into your boundary somehow, right? Now, one important note is this bit right here. This does not say that every boundary point of the image region came from a boundary point of the original region, S. Okay, so sometimes non-boundary points over here can be mapped to boundary points over here. But if you've got a boundary point back over here and your function is continuous, it's going to go to a boundary point over here. That's what it's saying. So here is an example. Think about the map f of x equals x squared. So think about good old x squared, one variable, parabola, vertex at the origin. Think about that for a minute. And think about the interval -1 to 1. So hopefully you can picture this, right? Can you think about, or can you find a point, what am I trying to say? Can you think of a boundary point of the image under this transformation that did not come from a boundary point of this interval? All right. So here I'm going to throw up the thinker for a minute. Okay, see if you can make sense of this and think about it. Right, now this one I want you to try to work out. So you may not even have to do it, you don't have to do any work. But can you think of a boundary point of the image of that interval that didn't come from a boundary point of this interval? Just to give you an idea, right? So the big takeaway here is that boundary points are going to go to boundary points, but that doesn't mean necessarily that all the boundary points came from boundary points. If you want that to happen, you actually need what's called a homeomorphism where you have a bijective function that is continuous and has a continuous inverse. All right, so moving along. Now that we know that boundary points are mapping to boundary points, the other theorem that we need is that continuous images of compact sets are compact. This is another powerful result. If I have a compact region and I have a continuous function that maps it somewhere, the result is still going to be compact. Compact for us means closed and bounded. So through a continuous transformation, you're going to end up with a compact space if you started with a compact one as well. And then furthermore, continuous images of connected sets are connected. So this means that if you try to map a region from over here with a continuous function over here, it's not going to break the region into pieces. So I can't start with a disk over here and then continuously map it into two disks over here. That's not possible. All right. So the book uses these theorems tacitly, but I feel like they are worth stating outright so that you can make sense of what's happening here. These are powerful results. They're what makes all of this nice. That's the best way to put it. So if it's going to make something nice, we should explain why it's actually valid. All right. Now let's go to an example. This is not one that I would ask you to do on your own first, but you are welcome to try if you would like. We're going to do this together. Here's a transformation T, and it's defined by these equations. And the task here is to find the image of the unit square. So the unit square, we're going to call it S. It's 0, 1 cross 0, 1, which is just literally the set of all points in R2, where U is between 0 and 1, and V is between 0 and 1. Okay, so a couple things I want to point out before we look at the rest of the example. Notice that this is a mapping from the plane to the plane. Here you put in coordinates U and V, and what you get out are coordinates X and Y. That's what's going on here. So that's why this is this is a vector valued function. It's telling you to go from this point to this point under the mapping. And we're going to see what these rules do to our unit square. How does it deform the unit square into this new region? So here we go. Now, because of that theorem, theorem number 3, I think, this image, or I should say, because T is continuous, it's going to map the boundary of the unit square into the boundary of the new region. all right? So that's what we're going to look at. We're going to look at the boundary and see where the boundary goes. And then the inside is going to go to the inside. So how do we do this? Well, yeah, first we're going to label them like so. S1, S2, S3, S4. And we're going to do this piecewise. This should look kind of familiar to what you saw back in section 14.7, where you were doing maxes and mins over a compact region, right? I think that's it. We're going to look and see where these boundary lines go. So here we go. If we're on S1, then that means V is equal to 0, right? So V is this axis, and when we're on this line, V is equal to 0. So plugging that into our equations, we get that x is equal to u squared and y is equal to 0. So these are now the parametric equations for the image of this line under the transformation t. So under the transformation t, this line gets mapped to what these are describing here. So what is this describing? Well, this is where you got to kind of dig back into your knowledge about parametric equations, right? So as u goes from 0 to 1, u squared also goes from 0 to 1. And as u goes from 0 to 1, y is just going to be remain fixed at 0. So S1 is actually mapped to the line segment connecting 0, 0, and 1, 0. So I don't want to flash forward to the final result yet, but what's happening is this line is really just getting mapped onto itself, except it's getting mapped onto itself, maybe moving a little bit slower than it did before. That's what this squaring is going to do. Okay. All right, now let's look at S2. What happens on S2? So on S2, u is equal to 1. So u is fixed at 1. And then when we plug that into our equations, we get these parametric equations for the image. X equals 1 minus v squared, and y equals 2v. All right, so again, think about what these represent parametrically. X is behaving parabolically, y is behaving linearly. This is a parabola. This is basically a parabola, and this is just a linear function, right? So what's happening is this line S2 is getting mapped to a parabolic arc, and the parabolic arc goes from 1, 0 to 0, 2. So in essence, this line is getting mapped to a parabolic arc that goes like that, right? And you can test it, like plug in the points, right? If I plug in v equals 0, right? Then I get x is equal to 1. And then over here I get 0, y is equal to 0. And then as you move from 0 to 1, you'll see that this line ends up going like that. So that's what it looks like. It's like a parabolic arc. Okay, moving along. What does S3 do? S3 is going to be similar to S1, S3 is going to be similar to S2. So on S3, V is equal to 1. Do I have that right? Yeah, V is equal to 1. So plug V equals to 1 into these formulas, and we get these parametric equations. So X is now u squared minus 1, and Y is 2u. And once again, this is a parabolic arc. This is describing a parabolic trajectory, right? And this one is actually going to go from 0, 2 down to negative 1, 0. So you can kind of put this together. We went this way, and then we went this way, and now we're going this way. And that's what's happening to these line segments under this transformation. All right. Lastly, what happens to S4? So on S4, S4 becomes, on S4, u is equal to 0. So when we set u equal to 0, we get x is equal to negative v squared, and y is equal to 0. So what happens to S4 is it gets mapped to a line segment going from negative 1 to 0, like so. Okay? Now, putting it all together, we get this. This is what it looks like all together. So S1 went like this. The image of S1 looks like that. S2 went like this. The image of S2 looks like this. S3 went like this. The image of S3 looks like that. S4 went like this. The image of S4 goes like that. So the transformation T is deforming the square into this kind of like scale-like region, this like rounded triangular thing, looks kind of like maybe like a fish scale or something like that, right? So that's what we're talking about when we talk about these transformations, taking this and mapping it to this. Maybe as a little, yeah, maybe as a little jump ahead for a minute. The utility of this is that oftentimes we may want to integrate on a region that looks like this, but man, that looks painful. Man, I don't really want to have to integrate on this. But if I can find a proper substitution, a change of variable that will let me take this and convert it into that, that would be really easy to integrate over. So hopefully we can. We just need to invert our function and take this region and deform it into a square. We just have to see how the integral is going to change when we do that deformation. All right, that's kind of the idea. And that leads us into the change of variables formula for double integrals. So here we go. This actually might be a good time to take a break. So let me just say that if you want to take a break for a minute, just let your brain kind of like uncook, maybe. Just let your brain recover for a minute. I'm going to drink some sparkly water and just hang out for a minute. Hmm. All right. Okay, so let's get started again. Hopefully you took a little break and you feel a little more refreshed. Now we're going to see some magic. So yeah, there you go. We're actually going to see some magic happen here. Let's investigate how an arbitrary C1 transformation would affect a double integral. So what if we didn't have explicit formulas for our transformation T? We just had a general structure for it. Well, here we go again, broken record time. If you recall the mechanics of the double integral, we're going to investigate how the transformation, how a transformation alters the area of a rectangular region. So going all the way back to like, oh geez, section 15.1 or 2. Here we go. So this is what we're going to investigate, and this is what the image is going to look like. So let S be a rectangle in the UV plane as pictured, and we're going to let T be a transformation that goes from the UV plane to the XY plane. That's T. So T takes a point U comma V and sends it to a point X comma Y. And we're going to say that the image of that rectangle S under T is called R. So simply put, T is mapping this rectangle to this little patch that you see here. Okay, we're going to label the lower left corner of R as x naught, y naught. And x naught, y naught is the image of the point u naught, v naught under T. So T takes this point and maps it to that point. That's what's happening, okay? Maybe I can zoom in a little bit, but yeah, so T takes this point and maps it to this point. That's what I'm saying here. Okay. The other thing we're going to do, there we go, is we're going to let the lengths of the sides of this rectangle be given by delta U and delta V, respectively. Wink, wink, wink. You can probably guess why that's the case, right? Now what we're going to do is describe a vector function. So this is the first time we've seen this in this course. We might have seen it a little bit back in like chapter 12, but this is going to kind of set us up for chapter 16, which is all about vector calculus. So we're going to describe or we're going to give a vector function that really describes what this region R looks like. And how do we do it? Well, we just basically have our component functions x and y, and they're going to say where you go to get to the image point, right? It's a vector function. So you plug in u and v, and it tells you where you're going to go to find the image point x, y. There we go. Okay, so kind of like, where does this thing go? Well, that one's going to go there. Where does this thing go? Well, that one's going to go there, and so on and so on. So this equation describes how to go from here to here using vectors. Right. Now, here's where it gets fun. So the equation of the lower side of S, that's when V is equal to V naught. So let me zoom in a little bit here, right? So if this is the point U naught, V naught, this is when V is equal to V naught, all right? Yep, there we go. So the image of this boundary line here is given by this vector function here. U is allowed to vary, but V is stuck at V naught. All right, so it's going to describe where this thing goes. It's going to go here. right? It's like curving that straight line. Now, the tangent vector to this image curve at this point is given by simply differentiating the vector function with respect to u. That's all it's doing. So differentiate this with respect to u. You get x sub u at the point, y sub u at the point, which is really just equal to this. That's what we're doing. So that will give you, do I have it on the next slide? Not quite. That'll basically give you the tangent vector at every point on that image, okay? Now, similarly, the tangent vector at this point to the image curve of the left side, this one, is what you're going to get when you differentiate with respect to v. So what you can imagine is like we are looking at the tangent vectors at these various points, there, and then previously they were here, here, here. That's the idea, okay? Looking at these tangent vectors. All right, now here comes the clever part. Here comes the clever part. So I want you to consider the vectors A and B that are given right here. And I'm going to describe what they are on this picture as you look at it right now. So what is the vector A? It's the vector that goes from this point to this point. So how do we describe that? Well, this is the point R of U naught V naught, and this is the point R of U naught plus delta U comma V naught. That's what this point is. It's what happens to the image of that lower line under the transformation R, under this vector function, okay? So how do we describe the vector A? It's just a displacement vector between this point, and that's what you see right here. That's the displacement vector. This minus this gives you the displacement vector. Now do the same thing for the vector B. So the vector B is this one right here, and it's the displacement vector between these 2 points. Notice this point right here is when you have V naught plus delta V, because that's the other side. Oops, sorry, that's the, wait, there you go. That's the left side of that rectangle we started with right here. That's this one. Okay, there we go. All right, so that's A and B. Now, here's where it gets fun. Since we know that these two partial derivatives exist, we can write them in terms of the limit definition of the derivative, right? Good old partial derivatives back into section like 14.3, I think. We know that these limits exist because these derivatives exist. And because of that, that means that we can actually approximate these vectors using delta u times ru and delta v times rv. So to get an approximation of these vectors, here we go. This is it. So this displacement vector, A, is approximately the same as delta u times ru. All right? Think about this for a minute. There's already a lot of stuff, so give your brain a moment to digest this, pause and think about it for a bit. Okay? There's a lot of technical stuff all coming together, all being called upon at the same time, so it's good to let it slowly digest. Just to reiterate again, remember that we have this result. So R sub u is equal to this limit, right? But because it's equal to this limit, and this is basically a linear approximation at the point, what we can do is we can say that R of u, we can say that R of u times delta u is about this, is approximately that. That's what this is saying here. And we can do the same thing here. RV times delta v is approximately this. That's what it's saying. All right, but what are these two things? This is B and this is A. So we can approximate those vectors A and B using the partial derivatives and this delta u, delta v. All right, now where the approximation keeps going, we can approximate R, which is the image of S under T, with a parallelogram given right here. So this green parallelogram approximates this region R. It's not exactly the same, right? It's an approximation. We're saying almost. This is one of the reasons why I say, don't abuse the equal sign. This is an almost situation. So this parallelogram you see here is roughly about the same as the patch that you see here. But there's some error involved, obviously, right? It's an approximation, okay? Now, We can find the area of this parallelogram using the cross product. So dig all the way back into chapter 12. We can find the area of this parallelogram by computing the cross product of these two vectors and taking the length. So this is what those two vectors are. And using properties of the cross product from back in 12.4, we can rewrite the area of the parallelogram like this. All right. Now, hopefully, if you see this structure, hopefully it kind of makes your head tip to the side a little bit. Hopefully this makes maybe squint your eyes a little bit. This looks a little bit familiar. Looks like we've kind of seen this thing show up before, right? So let's keep going. What does the cross product look like? What's the cross product look like? Use that determinant formula that we learned back in 12.4. We can write these vectors as vectors in R3 just by setting the third component equal to 0. Now we can use that determinant shortcut, and when you do that, what you end up getting is this. Wait, do I have a doubling here? Oh yeah, I got a doubling here. So you don't even need, wait, what am I doing? Oh, yeah, it ends up being the same. That's right. So you end up getting this, but this will end up being the same as this. So you basically get this matrix right here, and then you're taking the determinant of it. So what is the area of the parallelogram? Ooh, slight error here. Slight error. There should be a delta U delta V on here as well. So delta U delta V. That's the area of the parallelogram. So really what we're doing is we are computing the determinant of this matrix, right? So that's what's happening right here. We're computing the determinant of this matrix, and then we're taking its absolute value. That's what we're doing here to get this value right here. Okay, I'll rephrase this a little bit after the recording, but that's basically what's going on. Now, this matrix might seem like it's important because it is. This is a very important matrix. Notice it's basically a matrix that consists of the first order partial derivatives, okay? And that's exactly what it is. So this matrix is what's called the Jacobian matrix, or sometimes simply called the Jacobian. So the Jacobian is a square matrix of first order partial derivatives of some transformation t. So for two variables, it looks like this. We denote it with a j, maybe j sub t if you want to indicate what the transformation is. But it's literally just the first order partials, right? X is a function of u and v. Y is a function of u and v. So we have partial x partial u, partial x partial v, partial y partial u, partial y partial v. If you have a transformation of n many variables, n many variables, you can generalize this to that. So here is the Jacobian for a transformation of n variables. All right. We won't have to go that high, but you will, some of you will sooner than later, right? So the Jacobian determinant is literally the determinant of this matrix. So yeah, so this is the symbol that we use, that they use in the book to describe the Jacobian determinant. All right, so take the determinant of the Jacobian, and this is the symbol they use in the book to denote it. Okay, here's where I want to pause again just for a minute. Stare at this for a minute. Try to make sense of the notation because this is a lot of stuff coming fast. All right. Now, in general, for n variables, we write the determinant as this. So what's kind of nice is once you have the general theory, the notation cleans up very quickly. Sometimes going for the specific, like 1, 2, 3-dimensional cases makes everything look very, very messy. But if you look at the general case, everything is very clean. It's just a natural like generalization of stuff. So this is what we use to indicate the determinant of the Jacobian matrix. All right. Now, returning to our investigation, we can approximate the area, delta A, of the image patch using the parallelogram and the absolute value of the Jacobian determinant. So the area of that patch is about equal to this. Remember that the parallelogram is an approximation of that region, right? It's an approximation of the patch. So it's not equal to. But what we can do is we can rewrite the area of that parallelogram as this, and this is just using the notation we had a minute ago for the Jacobian right here. Take the absolute value of the Jacobian, or sorry, the Jacobian determinant, and then that's what you get. And here we're evaluating that Jacobian matrix at the given point, u naught, v naught. Now, okay, with this analytical result in hand, we can reconstruct our integral. So here we go. And we'll get our change of variable formula. Ready? Broken record time. So if we're given a continuous function f defined on a bounded region S in the plane, here it is. First, we're going to contain S in a rectangle, B, and we're going to define a function using an indicator function where it says yes on the region and no if you're not on the region. We're going to partition the rectangle B in the UV plane into a bunch of subrectangles, S sub ij, and we're going to denote their images in the xy plane by r sub ij. So what is t doing? T takes this little rectangle and maps it to that rectangle. That's what it's doing. All right. It's just like going this transformed rectangle, I should say. All right, and this is r sub ij. Now what we're going to do is we're going to apply that approximation that we had to each one of these little patches. We're going to do that for every single one of these image patches, right? That's what we're going to do. And by using an approximation and substituting it in, we get this. We get this double Riemann sum. But remember now x and y are in terms of u and v. And what is delta A? It's approximately this based on that parallelogram approximation. There we go. Maybe now you can see what's going to happen at the end. Taking the limit as m and n go to infinity, we get the following change of variable formula for double integrals. Here it is. Woof. Okay, so this is kind of the buildup. Getting to the punchline finally. So here is the general change of variables formula for double integrals. Here we go. Suppose that t is a C1 transformation whose Jacobian is non-zero, and that t maps a region S, maps a region S into the UV plane onto a region R in the XY plane. Suppose that f is a continuous function on R, and that R and S are type 1 or type 2 plane regions. Suppose also that t is injective, so we can invert it, except perhaps on the boundary of S. Then this double integral can be transformed into this double integral right here. There it is. Okay, that is an inverse substitution. So this is the general form of an inverse substitution. Oh yeah, that's what I'm saying right here. So take a look at this formula, okay? And what's just really amazing about it is I want you to compare this to the inverse substitution rule that we saw earlier in the lecture for single variable functions. Remember I said, think about this structure? Look, there's the inverse substitution and there's the Jacobian. That's the Jacobian for one variable functions. There it is, right? So it's just so beautiful. It's a really, really beautiful result. It is quite literally the generalization of an inverse substitution. That's what we've just done. So it doesn't matter what the transformation is, it just needs to satisfy some certain properties, and you can transform the region, and this shows you exactly how you're going to transform the integral, okay? So what is the big idea here? For those of you that have taken me for Calc 1 and Calc 2, I have mentioned this big idea many times throughout the courses. Here it is. Under a change of variables given by t, you're transforming the function and you're transforming the region of integration, but the value of the integral is preserved. Okay, this is the big idea. We changed the function. We changed the bounds. We changed the region over which we are integrating, but the value of the integral has been preserved under this transformation process, under this substitution, this change of variables, okay? What is the Jacobian? Well, the Jacobian determinant is encoding the factor that you need to scale those differentials in order to preserve the value of the integral after applying this transformation, all right? So this is one that I really do want you to think about, and not even just think about it out loud, but I want you to say this out loud so that it really sinks in and you're making sense of the big idea of what a substitution is resulting in. Okay, and now I want to, wait, go back to this. Now I want to just say this again. Notice here, everything has been changed. The region's been changed, the function's been changed, the differential has been changed. The one thing that has been preserved, the one thing that is equal here is the integral value itself. That is the purpose of this. So remember, the integral is our measuring device. And what we just did was we just found out how to basically measure using different units and preserve the length, or preserve the volume, or preserve the measure, preserve the amount. That's what it is. So you don't have to use inches. You don't even have to use the same shape of a region, right? It's kind of like, this can here holds 12 ounces, but this can, I could extend it much longer and shrink it in diameter and it would still hold the same amount. Or I could take this can and I could crush it down and the diameter would increase, the height would decrease, but the amount that it holds would still be the same. That is what we are doing here. We're saying, hey, it may be easier if instead of having this can, we crushed it down to something thinner. But if we crush it down, how does that affect the function? How does that affect the differentials? How does that affect like all those little pieces? This is how. This is how. Super cool stuff. Okay, so big idea. I hope that sinks in. Now we're going to use it. Here we go. So we are going to verify the change of variables formula for integrating in polar coordinates. And this is one where I do want you to try it on your own first. So think about it for a minute. Okay, say something out loud. I recommend maybe saying out loud the formulas for converting to polar coordinates. Right? And now try to work it out. So basically, take some region and some integral that's in Cartesian coordinates and convert it to an integral in polar coordinates using the change of variable formula that we just derived. All right, here we go. So in this case, what does our transformation t look like? It looks like this. X equals r cosine theta and y equals r sine theta. So that's what the transformation is doing. It's taking this and mapping it to x, and this and mapping it to y. What is the Jacobian determinant here? So the Jacobian determinant is this. We're going to plug in what these are. Remember, this is the matrix of the first order partial derivatives. So differentiate x with respect to r, and then x with respect to theta. You get this and this. Differentiate y with respect to r, and then differentiate y with respect to theta. You get this and this. Now do the determinant, or do that little like cross multiplication kind of thing, right? And then you get this, which is r. Okay, all right, here we go. Now everything changes. So substitute x for r cosine theta, substitute y for r sine theta, and then you're going to take the absolute value of the Jacobian determinant. So the absolute value of r, and voila, there's where that r comes from. The r that we saw earlier when we did this back in section, 15.3, I think it was. That's the r. That's where the r is coming from. Super cool. As long as r is not 0, yeah. Okay, now we're going to use it. Okay, so this one is one you're welcome to try on your own, but it might be a little bit tricky. For these problems, I find that it's easier if you can see an example first. But here we go. I want you to try to evaluate this integral here, where r is this trapezoidal region given by these vertices. Okay, and you're going to have to do a change of variable. Here's the tricky part. You're not told what the change of variable is. So you have to kind of make a guess at what you think would be an effective change of variable. Uh, think about it for a minute. All right. Then maybe say something out loud to yourself, maybe a groan. Who's to say? Okay, and now try to work it out on your own. And I will give you this hint. Remember, this is a two variable function. So you're going to have to pick a substitution for two variables. Maybe call them u and v. All right, and then see how you could let some part of this be equal to u and some part of it be equal to v, and then go from there. All right, here we go. So here's the basic idea. It's not easy to integrate this function with respect to x and y. You could kind of try to do it, even though the region looks nice. The function itself, it would be hard to integrate. There's not a simple substitution you can do. I mean, I should say, like, there's no simple way to do it. So what we really need to do is we need to choose a substitution that's going to make our lives a little bit easier. Now, the structure of the function itself suggests that we choose u to be equal to x plus y and v to be equal to x minus y, so that we can convert this into e to the u over v. And then that way we could integrate with respect to u and v in that case, and that should be a little bit easier to do, right? Okay. Yeah, because it's the fact that both of the x's and both of the y's are in the numerator and the denominator that makes this particularly hard to work with initially. But if we can get it to be a single variable in the numerator and a single variable in the denominator, that should be easier to integrate. So this is the substitution. Now here is the thing. This gives a transformation from the xy plane to the uv plane, but we need the inverse of this transformation, So this is that like going backward idea. We've got the fish scale, but what we really want is we want a square or something like that. So how can we, well, that's what we want to do. We want to transform the region so that the region is easier to integrate over in these new coordinates. Here we go. So using these two equations, we can solve them individually for x and y. When you do that, you get this. You're really just inverting them. So you could do it by substitution, for example. You could, let's see, what's a good example? I mean, you really just need x's and y's. So maybe if you add these two things together, you'll get u plus v, and then you'll get 2x. Yeah, you'll get 2x and the y's will cancel. Yeah, and then you can divide by 2. So that's how you do that, for example. So really you're just combining them to invert them in some way. So now we have our transformation that we want. This is the transformation t that's going to go from the uv plane to the xy plane. We've inverted the process. Here is what it looks like written out. Do this to u and v, you get x. Do this to u and v, you get y. All right? Now we compute the Jacobian determinant. So we compute the partials. So I didn't write that step on here, but compute the partial of x with respect to u, the partial of x with respect to v, and then partial of y with respect to u, partial of y with respect to v. And once you have those, you get these entries for your matrix. And now you can do the determinant again using that formula, and you'll see that you get negative 1/2. So in this case, negative 1/2 is the Jacobian determinant. All right. Now we've got pretty much all the pieces. We're only missing the new region. We have the transformation, we have the substitutions, we have the Jacobian, so we can compute, or we have the Jacobian determinant, so we can find its absolute value. Now we just need to redefine our region. We need the new bounds. So what we're going to do is, just like we did before, we're going to look at the images of those lines under this new transformation we've derived. Here we go. So this is where we started, and this is given by these equations here. Let me just run through them. So y is equal to 0, that's this, and then x minus y is equal to 2, that's this, and then x equals 0 is this, and then x minus y is equal to 1 is this, okay? And now we're going to see where those lines go under our transformation t, Oh, yeah, I should say, we're going to look for the pre-images, my bad. We're going to look for the pre-images under this transformation t, and this is what we get. So if you use those equations for x and y, this will give you the pre-image lines. This, and this. Okay, so u equals v, v equals 2, u equals negative v, and v equals 1, and you get this transformation here. There it is. So here's another point where I want you to pause and think about this. Maybe flick through the slides if you've got them opened up yourself. You might want to go backward and forward a couple times just to see what's happening. And then I'll show with my pencil here too. Right. Here we go. Okay, so just to kind of indicate what's happening, this line right here is getting mapped to this line right here. And this line right here is getting mapped to this line right here. This line right here is getting mapped to this line, and this line is getting mapped to this line. That's what's happening there, using the same technique that we saw earlier on in the section. Okay, what's great is that this is now what we're going to integrate over, and the nice thing is that this is what our integral looks like. So we just transformed this function into this function over our region S, but our region S is easy to parameterize, right? So we can integrate from left to right and then from top to bottom. That's what we're going to do. Integrate with respect to U and then integrate with respect to V. And that's what's going on here. Integrate with respect to U and then integrate with respect to V. Putting all the pieces together, this is what we're going to get. So here is our transformed function. Here's the absolute value of the Jacobian determinant to give us that extra factor, right? And then we found that that factor was -1/2, and this is our new integral. Now, after all of that, you should feel a little bit of a breath of relief because you're like, oh, okay, this one is not so bad, right? I can pull the 1/2 out all the way to the front, and then I'm just integrating e to the uv, and I'm integrating with respect to u first, right? So that's not so difficult to compute an antiderivative for. It's this, and then you just evaluate between u equals -v and u equals v, or evaluate at, I should say. Then you get this. It simplifies to this. You got a little v right there. And now you're integrating with respect to v. So again, this should be an easy integral to anti-differentiate, or an easy function to anti-differentiate, and you get this. Boom. All right. Okay. Moving along. Don't worry, there's not as much left as it seems. Change of variables in triple integrals. Here we go. So as you can imagine, the change of variables formula for triple integrals is similar. We're not going to go through the entire derivation over again. I strongly encourage you to go look back at the derivation that we just spent, 30 minutes going through, because it's basically the same idea. Let T be a transformation that maps S onto R. But now we're in 3 dimensions, so we've got a UVW space, and we're mapping into an XYZ space. Here are the parametric equations. The Jacobian determinant is denoted this way, except now there's 3 variables. It's the determinant of that, given by this. There we go. And then under similar hypotheses to what we saw before, this is what the change of variable looks like. Boom. So there it is. It's really just another inverse substitution. We're substituting in for x, y, and z, these new functions of u, v, w. But then we have to scale the volume in some way. We have to scale the volume appropriately, and that's where the Jacobian determinant comes from, and we take its absolute value, just so that there's no sign alteration through this process. And that's it. That's the idea. Now, change of variables in multiple integrals. So this is one where I will quite literally just state it. So I'll state the theorem, and again, the result looks very, very clean when you have n variables. So here we go. Let S be an open set in Rn. We're going to let T be a transformation from Rn to Rn. That is an injective C1 transformation, so continuous first order partial derivatives. The Jacobian of that is non-zero for every point in Rn. We're going to let f be a real valued function that goes from Rn to R, that is compactly supported, that is continuous, and its support is contained in this image. Then we can do this inverse substitution, and this integral can be rewritten like so. That is the formula for multiple integrals. And it's the same formula, really, same formula. A couple of small notes about these extra conditions here. Compactly supported just means that the place, I'll just say the place where the function is not zero, the closure of it is a compact region. I can explain it more in class if you are interested. And we need the support of the function to be contained in R. So it's got to be, yeah, where the function is not going to zero or equaling zero, we need that to be in R. But again, I can explain more of that in detail if you're interested in class. Okay, now, Here's the challenge. Use the change of variable formula for triple integrals to derive the formula for triple integration in spherical coordinates. So verify the formula that we got for spherical coordinates in the previous section, 15.8, all right? And that's what we're going to do in the activity. So let's go. Let's go. Yeah. Um, Thank you again. On that note, let's play. I tried to keep this as short as I could, so thank you for bearing with it. It is a very technical section. It is a difficult section. Give yourself time to digest it, but you will see these ideas come up a lot whenever you're doing multivariable calculus. I mean, this is the general change of variable formula for multiple integrals. That's what it is, all right? Okay, thank you again for listening, and I will see you all next time in chapter 16. So long.